This video is going to be the first video in my series from transistors to computer, where I'm going to be attempting to starting from transistors and working my way up to a small but functional computer. Now, in this video, I'm going to be using these 2N3904 transistors, not for a specific reason. You can just get them pretty cheaply, and I'll leave an Amazon link for them in the description below. So, first of all, we'll start off with what is a transistor. So, transistors, like this one, can be thought of as a switch for the purposes we're using them for. We have 3 pins here: the emitter pin, base pin, and collector pin. The collector pin can be thought of as like the supply, so we're just going to hook our current up to this, and then this can be thought of as the input. So when we put power through this pin, it'll allow power to travel from the collector here to the emitter here, and the emitter can be thought of as the output. So if I grab this over here, I've set up a little demonstration of how a transistor works. So we've got a transistor here, and I have the emitter or output pin connected up to this LED. Our supply here is connected there to power, and then I have the base pin or input connected up to this switch. And then I have this resistor here going from the emitter to ground, and that's not really necessary here, but it's used in some of the later things we'll go over in this video to prevent current from going from here to here when the supply isn't active. So as you can see, when we connect this here up to power through this switch, the light turns on. So now power is being allowed to pass through from here to here. And that is how we're going to make our logic gates today, which is what we're doing in today's video, basic logic gates. And you can see if we switch it back to ground, the LED turns off. Now, the most basic logic gate is the NOT gate here, or an inverter. So basically, whatever input we have on this switch, the opposite will come out on the LED. So for this video, we can think of power as a logic 1 and ground as a logic 0. So our switch, since it's connected to power right now, is a logic 1. So because it's inverted, it'll come out as a logic 0 here, which means the LED is off. And if we switch this switch back to ground, the LED turns on since we're giving it a logic 0. Now, this gate is also pretty simple. So right now, when the LED is on, the power is just going through this LED here and through the wire to the LED. But when we switch this switch on, power can go through the transistor here, and the easiest path for it to take, since there aren't any resistors, is just to go straight to ground through here, so it takes that path and the LED turns off. And that's a NOT gate. Now, the next gate we're going to go over is the AND gate here. So we've got an AND gate on the left. And how an AND gate works is if both of the inputs, so this one and this one, are logic 1s, or the switch is switched on, the output will be on. But if either of them or both of them are off, then the output will be off. So as you can see, if we turn one of them on, it's still off. If we turn the other one on, it's still off. But if we turn both of them on, the LED will turn on. So how this one works is we have the collector connected up to power here. So when both of the switches are off, the circuit stops here. It can't go any further because it can't go through the transistor. But when we turn this switch on, this still doesn't turn on because we have the output of this transistor connected up to the input or the supply current of this transistor. So, and this one's still off. So even though power is coming through here, it still can't come through this transistor and go through to the LED. And if we only have this one on, this transistor is never being powered, so nothing goes through the LED. But if we turn both of them on, power can go through this transistor and through the LED. And now you can see why I have resistors here. If I don't, when you turn this switch on, power can actually go from the base pin here through to the emitter pin here. But we have this to sync the current to ground when it has a resistor here. So when it's coming through this first transistor, it's the full 5 volts, but when we have a resistor here bringing it down, it can just be sunk to ground there. Okay, now over here on this other side we have our NAND gate. So there's in total 7 gates. We have the NOT gate, the AND gate, the NAND gate, the OR gate, the NOR gate, the XOR gate, and the XNOR gate. And other than the NOT gate, they're all in pairs of 2. For example, the AND gate and the NAND gate. And basically what a NAND gate is just the output is inverted from an AND gate. So you can see right now when these are both off, the light's on. And if one of them is on, the output will stay on. But if we turn both of them on, the light turns off. And this works similar to how our inverter works. When these switches are both off, power just goes through this resistor and through the LED. But when both of these are on, allowing power through the transistors, the easiest path is to just go through this wire to ground without going through the LED. So now we will move on to the OR and NOR gate. So the OR gate is if either of these are on, so this input or this input, the output will be on. So we can see if we have one on, it will turn on, or if we have both switches on, the output will also stay on. And how this is put together is we have this wire is connecting up the collector of both transistors, so both of them have power and always. And then we have the emitter connected up together and going through to the output, the LED here. So even if this transistor isn't on, power still gets to this transistor. And even if this transistor isn't on, power can still go from this transistor to the output. So if either of them is on, letting power through from this wire to that wire, then the output will be on. And this is similar to the NAND gate and the inverter, this NOR gate here, and that it's just the opposite of this. So unless both of them are off, the output will remain off. So this again works in the same way. Power can only go through to here, which is the easier path, if one of these transistors is letting it through. Otherwise, when it's blocked there, it'll just go through the LED here. Okay, our final set of gates are the XOR gate and the XNOR gate. And what that stands for is exclusive OR and exclusive NOR gate. And what the exclusive means is that if we have both of the inputs on, like we do here, the XOR gate will be off, where in this situation the OR gate would be on. So basically it's removing the AND portion of an OR gate. And because of that, This XOR gate is made up of a OR gate, a NAND gate, and an AND gate. And each of these inputs is fed into both the NAND gate and the OR gate. So the OR gate takes care of making sure that the OR gate's requirements are met. So if either one of these outputs is on, or both of them, this output will be on going to the AND gate. But this AND gate will only have its output powered if the NAND gate over here is also powered. And how a NAND gate works, it's always on except if both of the inputs are on. So that's how the AND functionality is removed. So if both of these are on, then even though this OR gate's output is powered, the output of the NAND gate is not powered going to the AND gate, so the LED remains off. And then lastly, this part of the XOR gate over here is just a double inverter buffer, and I'm only putting one of the inputs through it because that's what we need for this gate. It would probably be a good idea to do it for all of them, but this just prevents these two gates from shorting each other out because they have the same inputs going to both of them. And then this is the XNOR gate, so the output's just inverted. So this is on when we have either both of the inputs on or neither of the inputs on. And how this one works is instead of having our AND gate over here to combine these signals, we have the NAND gate. And what that does is, as we already saw, the output of a NAND gate is just the same as the inverted output of a AND gate. So that just means that the output of the XNOR gate here will just be the inverted output of the XOR gate. And I also have the double inverter buffer here, which just prevents these gates from shorting each other out. And those are all of the basic logic gates, and in our next video we'll move into making more working computer components with the building on these.